Hello, good day. Welcome back and please join me in to learn the embedded system design on ARM Cortex M4 series. Today we are on day 20. I hope you have been revising through the previous concepts and you are getting yourselves familiar with using different peripherals and different input output terminals and all the pins that's associated with the registers, and also how the bus connections are connecting from the high performance bus and the peripheral bus, etc. If not, please go back and revise so that you would be able to follow up with the rest of the session. Today is day 20 and we're going to learn about ADC. These are all the sections we're going to cover today. So you're going to learn about what is an ADC and what are all the registers that needs to be configured to do the conversion of it, and then you're going to write a program from scratch to set an example using a potentiometer. You're connecting to that ADC pin and you're going to adjust the potentiometer value and see the output at data console, ITM data console. Before jumping in, just a little bit about us. I'm representing A2DG. It's a startup by Anbukarasu brothers. That's my brother Alex and myself in 2023. Both of us gathered over 20 plus years experience, and we would really like to put it out there so that you can also be helpful and useful for you to be molded into a better professional. Our mission is to convey our knowledge and our experience to at least about 100,000 future professionals through our online courses. And the main advantage is you can study at your own pace at any time, wherever you are. So that is really good about it. A little bit about me. I am Arul Prakash Anbukarasu. You can call me as Arul or API, as persistent as I would like to be. I would like to share all my knowledge and get you to get into the habit of shaping yourself into a better professional. I have 20 plus years of experience working in various industries in Australia, Italy, Singapore, and in India. Majoring in all these industries in renewable energy sector on solar and wind conversion, power systems related to lead acid batteries, network embedded systems that related to ATMs, teller cash registers, point of sale machines, banking automation systems, and smart parking operations. And my expertise lies within these three: embedded systems, VLSI, and project management. I have a small announcement to make. I categorized into two different categories. One is the YouTube viewers and the other is internship professionals. In order to be eligible to get a free certificate, I will load all the video sessions in the A2DG YouTube channel. So please go through and you got to attend at least 28 classes to get e-certificate. At the end of every video session, there is a attendance link. You have to click that form and fill out your details and send it across to us. And that will count for your attendance for that day. And part of YouTube regulations, the videos can't live there forever. So after 2 or 3 days, unfortunately, the videos has to be removed. So if in case you have missed out to learn something and if you want to go back to review the videos, you can't, unfortunately. So that's why I strongly advise you and recommend you to join in one of our internship programs that would acquire you to get an internship certificate that is worth a lot, as I keep saying in every session, comparatively with the other engineers out there. Once they see this 30 days adventure that you already put through and you learned all the fundamentals, the basics of registers and how the peripherals and how the bus connections, everything works, and how the architecture, so forth. So it really it's a valuable thing, and you learn this in this 30-day challenge program. Not only that, you will have the separate login to log into our learning management system portal so that you can go view each and every day session. And also once you finish, you can click on the complete and that will count you as for the attendance. At the end of 30 days completion, after you hit the complete, the system will auto generate and give you the internship certificate. Not only that, you will get access, unlimited access to all the course contents. That includes all the PDF materials, the source codes, all the reference manual, the data sheet, and whatever that's related to this series. And also you can revise all your videos, so you can pause, you can go and do something, come back and rewatch it, or if you want to go back to few back sessions, you can also do that by reviewing yourself. So it is all out there for you to learn. And in case if you got stuck, please call our backend team and they would be able to help you to make you move along in your learning curve. I'm really keen to go and convert. Are you? Okay, shall we learn to convert from analog value to digital value? So that's what we're going to learn about. How you're going to convert 4096 to 10. That's the lesson you're going to learn. So let's get in and see how we can learn. First up, what is ADC? I'm sure everyone would know who are watching this and purchase this series. ADC stands for analog to digital converter. What it is just a system that converts an analog signal and that converts to a digital signal. Most of the sensors that we face in the real-time system will have some sort of analog signal, and to convert that to, you need to use a converter to connect to the microcontroller, so the microcontroller can understand what you're interfacing with and it throws you out as a digital value, because all microcontrollers are digital processors, so it doesn't understand the analog value. So that's why you need a converter to convert from analog signal and gives a digital signal as an output. For example, I just listed a couple of examples, such as the light entering through the web camera, that you are looking at me through this camera. So that receives all the video signals as analog, and the software built in, it does all the conversion and comes out in the other side as the good picture with pixels and all that. And then the second example, what I'm speaking now, the sound is picked by the microphone and that converts to the digital signal. So you don't get the signal interference and you can able to listen and hear me properly, which can be read by the STM32 microcontroller that we are learning about. So generally ADC is used commonly to measure any voltage from any sensor. For example, given here is a temperature sensor such as LM35, which can provide voltage proportional to the temperature. So just to give you an example, this is how the analog signal is sent in the input, and the ADC converts the analog and sends out as the digital form. As you know, digital values are only two. Either it is high or low, either it's 1 or 0, either it's VCC or ground. So likewise, it will convert from your input analog value and gives the output digital value. Now let's talk about ADC resolution. As you know, resolution plays a vital role in the conversion. So what is ADC resolution? The resolution plays a part in the step sizes, so the number of steps it takes to convert that analog to digital, it's called the resolution. And the STM32F411, it is a 12-bit ADC. It's a 12-bit resolution ADC, meaning it can detect 2 power 12 values, 2 power 12 bits, that's equivalent to 4096 bits, discrete analog levels, which is called the resolution. So you can convert 4096 values to digital value. Some microcontrollers will have 8 bits and 16 bits likewise. So if it is an 8-bit ADC, the number of steps it can generate is, it's 2 power 8, so you can get 256 steps. And if you calculate that into the step size, how many steps it takes to do the conversion, taking Vref as 5 volts, then you divide 5 volts by the number of steps, gives you the total voltage. So every step out of the 256, it's measured in 19.53 millivolts. So likewise, a 10-bit can generate up to 1024 analog levels, and ours is a 12-bit, and it can generate up to 4096 number of steps. And if you run from 0, it will go up to 4095 because you got start from 0. And if you divide that by 5 volt, you get 1.2 millivolt as the step size. So every step 1.2 volt conversion happens. And there is also 16-bit, and the number of steps for the 16-bit is 2 power 16, which gives 65,536 discrete analog levels. So this is about the resolution. Resolution is nothing but to convert in the form of steps from AD analog signals to digital signal. To do the conversion, you need to use few registers, and these are all the registers you're going to use today in the ADC registers. You need the ADC status register, you need the ADC control register 1, and there is ADC control register 2, that is ADC sequence 3, and there is a data register. First you need to check on the status, and then using the control register you're going to start the conversion and set the sequence and wait for the conversion to happen. And once it finishes its conversion, then through the data register you will read that value and see the output in the data console in the IDE. These are all the materials required to do the experiment. If you haven't bought it already, please do contact Pantex Solutions. They would be able to help you to acquire all of that. You need an STM32F411 nuclear board. You need a small breadboard. You need a 1 kilo ohm potentiometer. In short, you would hear it as pot. Everyone uses a pot. So 1 kilo ohm pot, or you can use a 5 kilo ohm pot or 10 kilo ohm pot. It's just a resistance, adjustable resistance, that's all you need. And some connecting wires, male to male, if you use sort of the breadboard connection with the pin, which I'll show you shortly. And this is the ADC schematics, as you can see from the picture. So this is the 3-pin variable potentiometer. The center pin, it's connected to the analog pin 1, and the first pin, which is on the left far hand side, the blue pin, that's connected to the ground, and then the other pin, it's connected to the ground. So you need only 3 wires and this potentiometer. So in real, this is a variable potentiometer, and you need 3 wires to connect these 3 to these 3 wires. So that's what it's explained. The center pin from pot, yellow wire, that is the second pin, is connected to PA1. That means port A pin 1. Yellow is connected to port A P1. So in the reference, in the diagram or in the board, it will read as A1. So you got 5 analog pins there. That's A0. So you need to connect to A1. And the first pin, the red pin, is connected to VCC 5 volts. That's a 5 volt. And the third pin, the blue pin, that's connected to ground. So this is all you need, and you can start to do your conversion with this. When you adjust, the value keeps differing. It depends on whatever value it reads from the adjustable knob, you get that in the output. But today I'm going to show you with a digital 3-pin. It's not digital, but it doesn't have a manual knob, but it has a screw instead. I'll show you. So this is more to understand about taking the reference input. So you have to set the ADC control register to start the conversion, and the initial transient you got to wait, and the number of bits, it depends on the ADC resolution here is 12 bits, so we're going to use a 12-bit transient. So you have to wait. Once you start the conversion starts, and you need to wait for all the bits, the step size, to go through and convert all of that. And once it finishes the stop transient period, then you can read the value at the end. So this is the reference input current for the typical ADC. This is the chart for the reference, with just saying start the conversion, wait for the conversion, and once the conversion ends, then you can read at the end of the conversion. this is the ideal transfer function, how that happens. So if you calculate the number of bits or number of resolution codes that you're going to use, so here they it's charted for x-axis and y-axis. So the x-axis is for analog input, the y-axis is for digital input. So 2 power n, so we are taking for 4 bits, so 2 power n will give 16 codes, that is 000 to 111, and you need to get a range of that and calculate the value 16, that's a 16. And if you calculate 2 volts, that is the FSR divided by 2 power 4, so the step size, every step size in this example, because you taking 2 volts as the reference, if it is 5 volts it will differ. So FSR stands for full scale range divided by the number of bits, that's the formula. And every step the ideal transfer is 0.125 of a volt jump, 0.125 of a volt. So every time you do it, so it converts from 00 to 111. So at the end here you will get the data. So that's how the real conversion happens. In other forms like a differential non-linearity, this is how it is measured, and you got to use this formula, and you got to use the long code and the short code, and the ideal code is DNL has to be set to 0. If it stays in the positive for the long period, that means that DNL value that you get from this calculation will be a positive one. But if it is a short ones like that, there are some few short ones, so it's a short one, that's a long one. If it is a short code, then the DNL value that denotes is a negative value. So this is how the linearity works. I'll take you to the functional block diagram, and I'll show you first where it's connected and which peripheral bus you're going to use. So first you need to check for the alternate function. You need to, as you know, the output mode register can be used as input mode, output mode, alternate function, and analog mode. So you need to set that pin to analog mode so that you can interface it with the ADC. So if you go to the reference manual page 198, you need to set it as analog, that will be 0011. So that's what you need to set. I'll show you when we go to the coding, I'll show you, but this is the first you need to initialize the ADC. To do that, you got to initialize these steps. First, enable the clock access for the GPIO port, because you are using port A1, so you need to enable the HB1ENR, and also the APB2, the ADC1 that's connected to APB2. If you come to the data sheet, I will show you, it's on page 15. So this is the functional block diagram. This is the ARM Cortex M4, and that's connected via the advanced high performance bus matrix, and it's connected to the advanced high performance bus AHB1. We're going to use the GPIO port A, that's PA1, that's we're going to use. And also the ADC is interfaced with APB2, so you need to enable the clock for AHB1 and APB2, and you need to set the program for ADC. So this is the one here. So enable that, and then you need to set the GPIO motor, which is if you go to page 198, you need to set the bits on the reference manual. GPIO motor. So we are using port 1, so that's port 0, GPIO port pin 0, that's pin 1, so we're going to use pin 1. You need to set this as analog, so 1 is analog mode. So if you set bit 3 and bit 2 as 1 and you set this as 0, then it reads as C. So that's what it's explained in the initialization steps. So you need to set that as C. Then before setting the conversion, you need to disable the ADC. So you enable the modder, and then you enable this, and then you need to reset the ADC by using the CR2. In this case we are using the CR2 register, and then you need to set the sequence first. In PA1 set the sequence, and then before you start the conversion you make sure you enable it. So this is the initialization to make sure the microcontroller knows it's the ADC value that's coming in. And to start the conversion you need to set the ADC1 CR2, which is this bit, SW start. You need to use this program. While of 1 PADC1 of CR2, you need to set this bit as 4. So if you set this bit as 1, so when you convert that to hex, these bits will be 0 1 0 0. So what is 0 1 0 0? It's 4. So that's why you write a 4, and the all the bits will be 0. So 1 2 3 4 5 6 7 zeros. So 4 will be followed by 7 zeros. 1 2 3 4 5 6 7. So this is how you start the conversion. So I given you another example how this conversion happens. So you start the SW start. So that's the bit, 30th bit. You need to set that to 1, and rest all the bits you need to set as 0. So when you convert to hex value taking 4 bits, you get this value 0 cross 4 followed by 7 zeros. So the bit 1, so if you take this 4, it's 0 1 0 0. By referring the table, you know that that's value 4, so you got to write that. And then wait for the end of conversion. So you need this register and check with the status register to see this bit, end of conversion bit, is completed. So 1 means conversion completes. If you set that to 0, that means it's not completed. So you need to set this bit as 1. So when you set this bit as 1, then what value you get? 0 0 1 0, that's 2. So that's why you write a 2 here. So this is how you have to write the program. Wait for the conversion, and then the next step is use the data register to read the value. So now let's go into STM32Cube IDE, and I'm going to show you from scratch how to write that program. But if you want to have a little break, so go and have that break, and when you come back we will learn how to program the ADC. Okay, I will catch you shortly in a tick. Go and enjoy that break. I'll see you shortly. Bye for now.